All right, let's start chapter 7 with 7.1 and 7.2, which is an intro to similar figures. So to review, we need to go over proportions since we'll be using those a lot with similar figures. Remember that a ratio compares two units to each other, and if two fractions or ratios are equivalent to each other, then a proportion exists. So this right here is an example of a proportion. You have two ratios, 2 to 5 and 6 to 15 set equal. Now if you remember, we would normally cross multiply here, so 2 times 15 is 30, and then we can check 6 times 5 is also 30. So that is an accurate proportion. Now also, if you were to simplify 6/15, you would get 2/5. So that's why they are the same ratio. All right, so just get some review of cross products. So I'll go over a couple of these examples with you. So A, we need to cross multiply here. Whenever you have a proportion, you cross multiply. So 6 times 4 is 24. Once we do one part of our cross multiplication, we put that down and then put an equal sign. And then we do the other half, which would be 5 times x. So that equals 5x, and we continue the algebra by dividing by 5, and we get x is 4.8, and that's our answer. All right, let's try B. So B, when we cross multiply here, this first wing of this butterfly, if you remember it like that, you have 3 being multiplied by the entire quantity of y plus 4. So we have to put those parentheses so that 3 is being multiplied by all of y plus 4, not just the y. Okay, and then your equal sign, and then you have 9 times y. So we can just write 9y. Now here, you would have to distribute, so you'll end with 3y plus 12 equals 9y, and we'll continue solving by subtracting 3y, so that 12 equals 6y, divide by 6, and y is 2. All right? So go ahead and try C and D as they are similar examples. All right, go ahead and check your answers to those proportions. So for C, your answer A was 63, and for M, this one, sometimes people get it wrong because they don't simplify that fraction or do their division wrong, but M was 1/4. Since we're working with fractions and ratios, a lot of times you may get a fraction or ratio as an answer, okay? All right, so similar polygons. When polygons have the same shape but are different sizes, okay, those are similar polygons. So two polygons are similar if and only if their corresponding angles are congruent. So angles are still congruent, and their corresponding sides, though, would be proportional because they would be different sizes, okay? So for instance, say if this one, that side was 1 and this larger figure was twice as big, this one would be 2. And say if these little ones were each 2, this would be 4. And if this one was 3, this one would be 6, because we're just doubling everything. And then each angle would be congruent, and so on around the shape. Okay, the angles are congruent, sides are proportional for similar figures. That's the difference between similar and congruent. So then you have this down here. The symbol for similarity is this squiggle right here. This similarity statement reads that quadrilateral ABCD is similar to GHIJ, that quadrilateral. And we can then line up our congruent angles and corresponding sides based on this similar figure. Well, if similar polygons have congruent angles, then I will just match up corresponding parts. So angle A is the first letter, so angle G is the first letter of the second figure, so those would be congruent. All right, so angle B would be congruent to angle H, angle C congruent to angle I, and angle D congruent to angle J. Okay, similar to when we were matching up corresponding parts of congruent figures. So now the corresponding sides, though, would be similar or in proportion. So if we match up AB, we would say it would be similar to GH. So still using those first two letters in the first two letters. So on. BC would be similar to HI. CD would be similar to IJ. And last but not least, AD would be similar to GJ. All right? Oops, there we go. And make sure these are all segments. So we're talking about, we have to use those hats when we're talking about those. All right, let's go to the next page. So really how you're going to see these corresponding sides matched up is in what we call an extended ratio. Which is basically like one big proportion. So we would match up, so AB, we would put it on top of GH because those ones matched up. And we would want the ratio of those similar sides to be the same ratio as BC to HI and to CD and IJ and to AD to GJ, okay? So all of those should come out with the same number. And we're going to do a couple examples that will show you what we mean by that. So example number 1, we're going to figure out whether each pair of these figures is similar. So we're going to start with these two triangles. We're going to first compare angles, which should be congruent. Okay, so let's make sure that we have congruent angles. So angle A right here says it is 30. That would match up with D, which they both say they are 30 degrees. So that one works. Okay, let's check angle B. Angle B should be congruent to E. And we don't have a measure for those, but we can find it because I know this one's 90 and this one is 30. So 180 minus 90 minus 30 means 60. And this is a 30 and a 90. So that one would also be 60. So angle B is congruent to angle E because they're all 60 degrees. And now angle C is congruent to angle F because those are both at 90-degree right angles. Okay? So all of our angles checked out. We had the 3 sets of congruent angles for a triangle because there are only 3 angles in a triangle. Okay, so now we have to do an extended proportion or extended ratio to compare our sides. So what we'll do is compare AB with DE, working our way around the triangle, and we want to see if that is proportional with BC to EF and AC to DF. So let's go ahead and start making those fractions. So AB is 12, DE is 9. So I'm just grabbing the lengths from the figure. And now BC is 6 and EF is 4.5. AC is 6 square root of 3. And DF is 4.5 square root of 3. So now what we would do is punch these into the calculator and see if they have the same proportions. So let's go ahead and do that. Alright, so when you punch these into the calculator, 12 divided by 9 comes out to 1.33 repeating. 6 divided by 4.5 comes out to 1.33 repeating. And this one right here also comes out to 1.33 repeating. So all of those ratios were equal, so our sides are proportional. Okay? So are the triangles similar? Yes, and the justification would be that the ratio of the measures of the corresponding sides are equal. So we want the sides are proportional, but the ratios of those sides would be equal. So like one side was 12 and one side was 9, so those weren't the same length, but in a proportion with the other ones, all the ratios were equal. And then we looked and our corresponding angles were congruent. And that makes triangle ABC similar to triangle DEF. Alright? Alright, example number 2. Determine whether these figures are similar. So compare angles. Well, every angle in both of these figures are right angles. So all are right angles. So we're good. 90 to 90, everything is all congruent. Alright, so now the corresponding sides. So if I want to grab 7 from this one, I'm going, which is the bigger one out of these measures of 7 and 6 on this first quadrilateral. So then I grab the bigger one over here. I'm not going to grab the big one here and the small one. So I'll grab 7 to 6, and I want to see if that is similar or the same ratio as 6 to 5. Okay, so this 6 would actually go with this 5, and this 5 with this 6, but they're all the same lengths. All right, so now we see if those ones are the same. 7 over 6 comes out to 1.166 repeating, and 6/5 comes out to 1.2, which is not equal. The ratios are not equal. So no, not similar, because the ratios of the sides were not equal. All right, so our angles matched up, but our sides didn't. So then we just scratch it, we're done. These are not similar figures, okay? Let's go on to the next page. Scale factors is what we're going to be using to talk about how much larger one is compared to the other. So for special effects used in movies, a scale model of an SUV was 22 inches long and was made to look just like the actual SUV, which was 14.5 feet long. So what's the scale factor of the model compared to the real SUV? But remember, we have to compare feet to feet or inches to inches. So let's just put everything in inches. So we got to take 14.5 feet and multiply it by 12 inches, that is in a foot, and you get 174 inches for the real SUV. So now it said compare the model compared to the real. So we're going to put the model on top, and that is in inches. And we're going to put the real SUV on bottom because we're creating a ratio here for our scale factor. All right, so the model was 22 inches, and the real one is 174 inches. All right, you always will want to simplify your fractions in your calculator, and your calculator will do that for you. If you type in 22 divided by 174, and then math, enter, we'll get the fraction for that, the simplified fraction, and you get 11 over 87. All right? So that is the scale factor of the model to the real SUV. You may also see this written as 11:87, okay? They can write a scale factor like that as well. So now the scale factor does depend on the order in which you're comparing. So this said model to the real. So if we wanted to compare the real one to the model instead, it just becomes 87 to 11, or 87 over 11. The numbers don't change, we just switch the order in which we write them. Okay? So proportional parts. This example, this is how you'll see a lot of the problems that you'll do with this section with similar figures. So we're going to write a similarity statement. So just so we can know which letters we are matching up, let's just go around these figures. So R, S, T, U, V would be similar to A, B, C, D, E. Okay? So now we're going to find X, Y, and UT. So in order to start this, what we want to do is look at where some sides match up. So, and I want one that will be all numbers, so I'll have a ratio. So 18 and 4 are both in the same part of both of these figures. So that will give me my ratio or scale factor to begin with. Okay? And now I'm going to match it up with, I want to find out X, so I want that to be in my problem. And that's on the same figure as the 18 was. And then 3 is what it corresponds with on the other shape, so I'll use that. All right? And now we'll cross multiply and solve. So 18 times 3 is 54, and 4 times X is 4X. So we divide by 4, and X is 13.5. So we've got one of our answers. Now, finding Y, I'm still going to use 18 over 4. And now, instead, I want to find Y. So, oops, there we go. So I'm going to use Y plus 2. And on the other figure, it corresponds with 5. So those would be the similar sides. So Y plus 2 on top and 5 on bottom. It matters that all along the top is coming from one figure, and all along the bottom is coming from another figure. If you mix and match, it won't be accurate. Okay, so cross multiply again. 18 times 5 is 90, and we'll have to distribute here. Okay, so when you distribute, you get 4y plus 8 equals 90. We do some algebra, and we get y is 20.5. All right, so we've got x and y, and now we need to plug it back in to ut right here, which is just y plus 2. So ut is 20.5 plus 2, which is 22.5. All right, so we got all of our answers. And now it's asking to find the scale factor of polygon RSTUV to polygon ABCDE. So I want to pull a measure from RSTUV, which is 18, and pull a measure, the corresponding one from ABCDE, which was 4. So it's what we've been using to do all these proportional parts, but I'm going to simplify this, which is 9 over 2, or 9:2 for our scale factor of RSTUV to polygon ABCDE. Okay? Last part, last two examples. Example 4 and example 5 on the back use these proportions to solve types of real-world problems. So if you were trying to enlarge a figure, triangle ABC is similar to triangle XYZ with a scale factor of 2/3. So it is going to get 2/3 bigger than ABC. So if the lengths of the sides of triangle ABC are 6, 8, and 10, what would the lengths of the sides of triangle XYZ be? So what we're going to do is we know that with triangle ABC, we know one side is 6 and we don't know the other one. We're going to do this 3 times because I know the other side is 8 and I don't know what the next side is that would correspond with that. And then we have 10 to Z because we don't know what the last side is. All right, and those are in a ratio of 2/3. So that's how we're going to set up all of these proportions. And we will cross multiply all of these. So 6 times 3 is 18 equals 2x. So x is 9. We've got 8 times 3 is 24. And we'll have that equal to 2y. So y is 12. And then 3 times 10 is 30 equal to 2z. So z is 15. So the sides of x, y, z would be 9, 12, and 15. Okay, those would be the 3 sides that would be similar to triangle ABC's sides of 6, 8, and 10. So it did get a little bit bigger. All right, so now using the similarity, think of if your class is making a rectangular poster for a rally. The poster's design is 6 inches high by 10 inches wide, and the space allowed for the poster is 4 feet high and 8 feet wide. So what are the dimensions of the largest poster that will fit in the space? Okay, so first things first is you should figure out if you can fit the whole space. So determine if you can fit the whole space, or at least how large you can go. Okay, so we'll take our height first. So the height, the largest we want to get is 4 feet, and we're going to change that to inches, so times 12 is 48 inches. All right, so 48 is how much I have, and I'm going to divide that by the height of my original design, which was 6, so I can go 8 times bigger. All right, now with my width, I have 8 feet available, which is really 96 inches. So 96 inches divided by the 10 inches that my original is 9.6. So I can get 9.6 bigger. So if I go 9.6 bigger, I'm going to overflow the size of that wall there. So I have to use the smaller one. So the biggest I can go is 8 times bigger. Okay? So now that you know how much bigger you can go, step 2 would be to actually enlarge it. So now we're going to enlarge it. So we know that our height will go 6 times 8 being 48 inches. So I'm actually going to take up that whole space. And then, but our width is 10 inches. And we can only multiply that by 8, even though I could go 9.6 to fill the whole space, but we got to keep it all the same size. All right, so that would go to 80 inches. So the poster, the largest we can make it is a 48-inch by 80-inch poster. Okay. The reason why we have to go the same length out is think about like if you're enlarging a picture on Word or on PowerPoint when you're making a project. You go from the corners so that you enlarge the width and the height at the same time, okay? So it doesn't mess up your picture. So anyways, determine if you can fit the whole space and then enlarge it by how much you can. All right, come in with your notes filled out and we'll go over some more similar figure stuff.